Okay, good afternoon, everyone, and welcome to this special ICTS public lecture that we are having as part of our celebrations of the 100 years of quantum mechanics. So this is a week-long meeting and many exciting talks. And as part of that, we are very fortunate to have a number of very distinguished and some of the scientists who are really pushing at the frontiers of quantum mechanics. And so today, I'm very delighted that Professor Vedika Khemani agreed to give this public lecture as part of this occasion. We also will have another related to this program public lecture on Saturday, 18th this month, this Saturday, at 5 p.m. at the Christ University campus. This will be our C.V. Vishweshwara lecture, but now folded into this program. It is also given coincidentally by another professor from Stanford University, Professor Roger Blanford, on a very different topic. It will be on quantum astrophysics and cosmology. So this will be kind of the very small quantum and small to intermediate maybe, and that will be from the large to the humongous. Anyway, so we'll be seeing through, I hope many of you will come for these public events, for the other public event as well. And many of the talks in the program are also being live streamed on YouTube. So if you would like to watch some of them, so for instance, tomorrow there will be a whole day of talks on quantum computing, information, and both experimental and theoretical. If you go to the web page of this program, you will see a link to the YouTube channel where you can watch these live streamed. So I encourage you to do that as well. So I'm very glad to also welcome many people from St. Joseph's College, Christ University, MCC, and Chanakya, and the IAQT program at IISc here. So thank you very much. ICTS organizes a large number of such public events. I hope you will join. And this year we will have several others as part of the Year of the Quantum. So please look at our webpage and I hope you'll come for these events. Now I'll hand it over to Professor Abhishek Dhar from ICTS, who will give an introduction to the speaker. But before that, I just wanted to give a small token memento to Vedika on behalf of ICTS.
Yeah, good afternoon, everyone. So it's a great pleasure to welcome Vedika Khemani. So Vedika is an associate professor of physics at Stanford University. She's a theoretical physicist who works at the interface of quantum information and condensed matter physics. She received a PhD from Princeton University in 2016 and was a junior fellow at Harvard from 2016 to 19. Vedika, she works in a lot of broad range of very exciting topics in like foundations of non-equilibrium quantum dynamics. And I think today she will talk about things like quantum crystals, time crystals, and many body localization, quantum scars, and so on. It's a huge range of areas in foundations of quantum dynamics. Vedika, for her work in non-equilibrium quantum dynamics, has received a number of very prestigious awards, including the Breakthrough New Horizons in Physics Prize and the Macmillan Award. And most recently, I think just last week, she received the Infosys Award in the physical sciences. So it's a great pleasure to have her here at ICTS, and today she will talk about the many-body physics of computation.
Yeah, thank you very much for that kind introduction and for the opportunity to speak at this historic celebration of quantum mechanics. Thank you all for being here and traveling, battling Bangalore traffic to get here. I'm really excited to share some beautiful and transformative ideas today in physics, going back several decades. Much of what I'll talk about is actually not my work. It's honored the celebration of quantum mechanics. So I'll talk about some very, very nice ideas which have shaped our modern technological age. and which in turn are inspiring new questions. The machines of today are inspiring new questions and new theoretical problems which promise to shape a boundlessly exciting future. So, to begin, let's address a fundamental point. Actually, could we have this light off and those lights on, just to get the contrast to the slides? Okay. And are the lights over there on? Okay. So to begin, let's address a fundamental point, right? Computation at its heart is deeply physical. It's easy to think of computation as abstract. You know, you're thinking of some algorithms or you're thinking of data, but every single computation under the hood is a manipulation of a physical system. For instance, in classical computers, we process data by flipping classical bits, zeros and ones. But again, under the hood, these classical bits are the states of some physical switch of some transistor device made up of some physical material, such as silicon, okay, and composed of billions and billions of interacting electrons and atoms. All of that goes under the hood to give you a single binary digit, which is 0. Okay. Likewise, in quantum computers, we talk about quantum bits or qubits. And these are strange particles governed by the beautiful laws of quantum mechanics. And unlike a classical bit, which can be 0 or 1, a quantum bit isn't in a definite 0 or 1 state, but it's in a superposition of being in 0 or 1. Okay? And it's this superposition of many interacting quantum particles that underlies the promise of quantum computing and quantum technologies. But again, you know, we think of this quantum bit as this abstract object, but under the hood, it is composed or it's extracted from some underlying many-body system, which could be, for instance, an atom with many different electrons and other particles, or it could be some system of ions, it could be a superconducting Josephson junction. So there are, again, physical underlying systems which you use, and from those physical underlying systems, you extract some effective or emergent particle, which is going to form your quantum bit or your classical bit. Okay? Even the limits of computation are dictated by physical laws. For instance, Landauer's principle tells us that erasing bits of information generates heat. And this underpins what, you know, fundamental energy requirements for running quantum computers, for running any computation. Likewise, Moore's law, which is doubling of computing power every 2 years, is now starting to show signs of slowing down as we approach the physical limits of miniaturization. So physics doesn't just underpin computation, it really sets the rules for what's possible. And the theme that I want to emphasize throughout my talk today is that computation isn't just about the physics governing individual particles, but it's fundamentally about what happens when many particles interact. For instance, as I was saying, if you take this transistor and you zoom in further, this is composed of some material like silicon. Silicon now has billions and billions of atoms. Each atom has electrons and protons and neutrons all interacting with each other. And from all of this many particle interaction stems your classical bit, okay? So the study of such problems of many interacting entities are what physicists call many-body problems. And a theme that I'll emphasize throughout my talk is how emergent phenomena coming from the study of many-body problems is shaping technology and practical applications all around us today. Okay, so let me take a minute to talk about this beautiful idea of emergence. Emergence is a powerful scientific concept that cuts across many different fields and happens across every stage in the evolution of our universe, from the formation of galaxy clusters to the description of ant colonies and bird flocks in nature to the evolution of, you know, cognition and life itself. Evolution is the idea of complexity from simplicity, okay? That interactions between many simple particles can create some entity for which the whole is much bigger than the sum of its parts, okay? Emergence reveals utterly new phenomena that you simply cannot understand by studying one or a few simple entities alone. For instance, if you think of this bird flock and you think of what an individual bird in this flock is doing, it's just following some simple rules, right? Like don't flap my wings into my neighbor, stay close to the flock. But with each bird following these simple rules, you see that the flock as a whole evolves as this beautiful, coherent entity, okay? In other words, more is different. Lots and lots of simple interacting entities can give a plethora of beautiful, amazing emergent phenomena, and this amazing emergent phenomena is driving all of the wonders of our world today. Okay, so I'll organize my talk around 3 vignettes. These are based on many body systems of interacting quantum particles. Okay, they could be electrons or what are called spins or qubits. And when we think about many particle systems of these interacting entities, they can organize themselves into different phases of matter. Okay, we're all familiar with phases of matter like solids, liquids, and gases, but you can get many, many more exotic possibilities, and it's these possibilities that are driving technologies from classical computing to artificial intelligence and more recently, early developments in quantum computing. Okay, so that's going to be the majority of my talk. But what I want to really foreshadow here today, because I don't know if I'll have time to get there, is that these new paradigms for computing and these new technologies that we're developing today are in turn allowing us to probe many-body quantum matter in completely new regimes, okay? And these are regimes which need not exist in nature even, but which are made accessible to us with new developments in quantum computing and quantum simulation platforms. So for instance, these types of devices give us access to studying many particle quantum systems which are strongly out of equilibrium. Okay, when you think of some phase of matter or quantum material existing in nature, it's an equilibrium state. It's just hanging out there in nature. But these quantum devices allow us to probe strongly out of equilibrium quantum dynamics. They also allow us to engineer completely new and exotic types of geometries in which these systems can live. Okay, around us, we all live in three Euclidean dimensions, but these new devices are giving us access to matter which are not governed by those same rules or not constrained by those same rules. So this is leading to fundamental new theoretical questions about what possibilities, what new types of phases can exist in these new settings, which in turn can inspire the next wave of developments in the next century, okay? But to see how these ideas have evolved over time, let's step back to start with their roots in fundamental theoretical developments going back over a century. Okay, so we're here celebrating the first quantum revolution, okay? The first quantum revolution refers to the period when quantum mechanics fundamentally transformed our understanding of our physical world, revealing the rules that govern matter and energy at atomic and subatomic scales. So arguably, this revolution began with the work of Planck in 1900. Planck was studying black body radiation, and he introduced this idea that energy is not continuous, but rather it's quantized and comes in discrete packets. Okay, so this I think was the first like really clear introduction of this concept of quantization into physics. And this radical idea was then built upon by Einstein in 1905, just a few years later, where he used it to explain the photoelectric effect, for which he got the Nobel Prize. And in this work, Einstein proposed that light itself is quantized, consisting of discrete particles called photons, okay? Now, of course, we know that in quantum mechanics, there's this fundamental idea of wave-particle duality, where light is simultaneously a wave and a particle, and familiar things that you might call particles, like electrons, are also simultaneously have a wave description, right? So this was really transformational and set the foundation for the century of quantum mechanics that was to follow. was continued on in the early 20th century. You know, our understanding of things continued to evolve. One important milestone here was that Bohr proposed his model of the atom, which showed that electrons actually, again, occupy discrete quantized levels within an atom. Okay, that was a big update to our understanding from thinking of energy levels as continua to thinking of energy levels as discrete and quantized. Then in 1925 to 27, you know, Heisenberg, Schrödinger, and Dirac really set forward the theoretical formulation, the rigorous mathematical theoretical formulation of quantum mechanics. Okay? Heisenberg in 1925 proposed matrix mechanics, and Schrödinger, just a year later, proposed his wave mechanics, which says that particles should be governed by wave functions, which evolve according to Schrödinger's equation. And later it was realized that these two formalisms are really identical. Okay? So this kind of put quantum mechanics on very firm theoretical footing, and this development here is what we're celebrating 100 years later. Okay? Good. So what I said so far, these fundamental foundational ideas, they were about the behavior of one or a few particles. Okay, but again, very early in the 20th century, people already started thinking about not just individual particles, but also the behavior, collective behavior of many, many particles. Okay, and this led to the development of the concept of quantum statistics. And it was realized that there are two fundamental types of particles: bosons, named after S.N. Bose, and fermions, named after Enrico Fermi, which compose all of matter and energy, but which behave according to very, very different rules. Okay? In 1924, Bose and Einstein developed the theory of Bose-Einstein condensation and showed how bosons as fundamental particles have this remarkable property that systems of many, many bosons can all collapse into the same quantum state, okay, and act coherently as a single quantum entity. And this underlies this Bose-Einstein condensate underlies the working of the laser, which is ubiquitous in almost every technology today. Okay? On the opposite end of bosons are fermions. Okay, so fermions are very, very antisocial. Bosons all pile onto the same state, but no two fermions ever want to be in the same state. Okay, fermions are governed by Fermi-Dirac statistics, and matter particles like electrons, all matter particles are fermions. And this Fermi-Dirac statistics really underlies our understanding of the behavior of electrons in solids and led to the development of much of what followed in the structure of atoms and in solid state physics. And indeed, like very soon after, in the development of what's called band theory. Okay, so band theory describes the behavior of electrons in a solid. A solid is some material. It's composed of many, many billions of atoms. These atoms are positive ions arranged in some regular grid, and surrounding these ions are again, billions of more interacting electrons, okay? And what's amazing is that you can take this system. It's a really, really hard system, okay? Even keeping track of the state of all of these atoms and electrons is just hopelessly impossible. They're all strongly interacting with each other via Coulomb's interactions. So the fact that we were able to take this really complex system and reduce it to a form where we can actually make pictures like this, which you see in high school textbooks, is just, it's incredible that we could do this, okay? But what band theory tells you is it's a way to, there's a lot of approximations that go into it, which work miraculously well for various deep reasons. But band theory tells you that if you look at the energy level of a system of many electrons, if you look at the energy levels in this in this solid, then while a single atom has discrete energy levels, okay, that was what Bohr showed us. When you have many of these atoms all interacting together, these discrete energy levels blend into nearly continuous energy bands, okay? And these energy bands tell you the states that your electrons can occupy. And being fermions, they're only going to occupy one state at a time and keep climbing up in energy. They can't all collapse into the lowest energy state. Okay? So you're going to fill up bands with electrons, and this process of filling up bands really sets our understanding. Just these simple pictures can predict a lot about lots of materials all around us. Okay, so you have what's called a valence band. These are electrons which are very tightly bound to the atoms, and they're not free to move around. And then you have a conduction band. These are electrons which are not really bound to anything, and they're responsible for conducting electricity and for conducting charge. And in between these, there's a band gap, okay? So in a metal, this band gap is 0. The conduction band and the valence band are overlapping, so current flows freely. In an insulator, the valence band is fully filled, and then there's a big energy gap. You need a lot of energy to get into this free-moving conduction band, so everyone remains tightly bound, and you don't conduct any energy, or you don't conduct any electricity, okay? In contrast, in a semiconductor, you have a band gap, but this band gap is very small, okay? And what this small band gap means is that by injecting just a little bit of energy, say by applying a voltage or a pulse of some kind, you can promote electrons from this valence band into the conduction band. That means that you have a switchable conduction. You can control, you're going to go in and act with a little bit of voltage, and using that control, you can promote electrons and make them conducting. So this switchable conduction, which leverages this property of many-body physics and band theory, is really what's underlying the transistor. Okay, so silicon-based transistor, silicon is a semiconductor, this underlies this transistor, and a switch in a transistor is the switchable control over the flow of electricity. Okay, so building on these developments in band theory, the transistor was invented in 1947, which ushered in which established solid-state physics as a distinct discipline in the middle of the 20th century. And of course, the transistor then became the fundamental building block of all modern computing and electronic devices. Okay, so today's chips contain billions and billions of transistors packed in some area which is smaller than my fingernail. And this scaling, which is again driven by Moore's law, has powered decades of progress and led to the development of a host of technologies, all of which rely on the collective emergent behaviors of systems of many, many interacting particles. Okay, but the breakthroughs enabled by the first quantum revolution certainly didn't stop here, okay? We're now in the midst of a new wave of computation driven by artificial intelligence and machine learning. And artificial intelligence systems, like neural networks, are dramatic examples, again, of emergence. These systems represent a profound change in how we compute. Okay, we're now moving away from a paradigm of explicitly storing, processing, and retrieving information like bits in memory to distributed representations and emergent intelligence. So the present wave of computation is not just about let's scale our hardware, let's pack in more transistors onto a chip, but it's about creating new classes of systems that I think are going to be soon much more intelligent than anyone in this room. They're about creating new classes of systems that can adapt, learn, and make decisions. And this is really a remarkable emergent phenomena. And to understand how this happens, let's take a minute to see how we go from classical bits to emergent neurons, okay? So let's start with classical bits again. In classical computing, information is stored explicitly, okay? If you want to represent the number 4, you represent it in binary as 1, 0, 0, okay? And then these binary digits are again encoded in the states of some transistor, and you have transistors in a chip. So each bit is independent, and the information is retrieved exactly as it was stored. On the other hand, in a neural network, information isn't stored explicitly, but it's rather distributed in the collective interactions of the system. Okay? When a neural network learns to recognize a digit such as 4, this digit isn't explicitly stored anywhere. Right? Rather, the concept of 4 is distributed across the many, many, many different neurons in this network, so that when you feed this network an input, it learns to recognize this digit, which is 4. Okay? Every single node in this network, which is what I'm calling a neuron, this is just a it's just a neuron here is just a number, okay? The neuron is characterized by this number A. It's just some number between 0 and 1, okay? And then this neuron takes in the states of its neighbors. Okay, what are the neighboring neurons doing? How am I connected to them? What's the weight of my connection? And then, sorry, this should have been some function. Okay, then it computes some function of these weights and its neighbors, and then it sets its own state. Okay, so each individual neuron is just governed by some very, very simple rules. Okay, there's no number 4 or any part of number 4 in any one individual neuron. But together, when you look at the collective state of all of these neurons, then this information is encoded and distributed across this network of interactions. Okay? This idea of distributing information across a network of interactions both illustrates the idea of emergence and also points to a robust encoding of information, which is going to have close parallels to what I'll talk about in a few slides on error correction in quantum mechanics. Okay? So because the concept of 4 is encoded in this joint state of so many different neurons, okay, you can have this network change around a little bit. Okay? You can have some neurons become faulty, some weights change a bit, but it's not going to lose its concept of 4 with some small changes. Okay? This, you can recognize fairly bad handwriting and still recognize the number 4. So this kind of distributed encoding of information also comes with some robustness. And that's going to be an important concept. So I just want to step back here and talk about the 2 different levels of emergence that we've discussed here so far. Okay? On one hand, we have this system of billions of atoms and electrons, which is forming the state of a transistor. And this transistor is giving me access to bits. Okay? After that, I forget where these bits came from. And I look at these neurons. These neurons are just digits, they're numbers. So every number is represented in memory using probably several transistors, each of which relies on billions of electrons. But now I look at this system of neurons, which are just numbers, and see how all of the systems of these numbers are all interacting with each other. And lo and behold, I get memory, and I get much more than memory these days. This is the simplest neural network that I'm illustrating for you. I get memory, I get reasoning, I get everything that we rely on ChatGPT for or amuse ourselves with ChatGPT for these days, just with a pattern of simple connections like this and numbers interacting via weights. Okay? I want to emphasize here that these breakthroughs that are underlying modern AI, they also have their roots deep in many-body physics. Okay, so this idea of having this network of interactions and using it to encode memories and retrieve memories and learn things and encode information, this again goes back to work from several decades ago in many-body physics on the topic of spin classes. Okay, so one of the most fundamental quantum attributes is that of spin. An electron carries something called a spin. There's no classical analog for it. You can represent it as the spin of an electron gives it 2 states. It can be in spin up or it can be in spin down. Okay, these are classical spins, so they only have 2 states, which are 0 or 1. If I was talking about quantum spins, then I would model this as something, again, living on what's called a block sphere, and then it can be in any superposition of 0 and 1. But in a spin glass, these were models that were developed in the 1970s to think about disordered spin systems, and also actually as a toy model to understand window glass, which is still a problem that is very rich in the number of things that we don't know. But in spin glasses, you have a system of spins. These are little magnetic moments. You can think of them as little magnetic moments. And they're all interacting with each other via this network of interactions. And this is what's called a frustrated system, okay, where sometimes you have some interaction, which is in blue, which wants these spins to align with each other. So you want two neighboring spins to both be up. And other times you have an interaction which is red, which wants the spins to be anti-aligned, one to be up and one to be down, okay? And then you have all of these different connections going every which way. So by the end of it, any given spin has some neighbors it wants to be aligned with, other neighbors it wants to be unaligned with. So it's very frustrated, it's very complex. And in various classes of spin glasses, what you know is that if you look at the energy, you can model these interactions via Hamiltonian. And if you look at the energy landscape of this Hamiltonian, what you'll find is that it's a very, very rugged energy or free energy landscape. And it has many, many local minima, okay? And these local minima are associated with particular patterns of spins. And these patterns can be stored robustly, okay? So if you want to recall this particular pattern that lives at the bottom of this minima, and there's some heat in the system, there's some spin flips coming from thermal fluctuations, maybe you mess up this pattern a little bit, well, you can kind of cool and find your way back down, and you can recall this pattern here, okay? Now, Hopfield Networks. So Hopfield won the Nobel Prize this year in physics, okay, for his work on these networks. Hopfield networks are a very close adaptation of this physics of spin glasses, okay? Instead of thinking about spins, we can call these neurons, okay, which are on or off. In Hopfield's network, they also had just two states, which were on or off. These are classical bits. And instead of calling these magnetic interactions between spins, we can denote them as weights of different synapses, okay? But the physics is really the same. And what Hopfield showed is that these interactions, these JIJs, these couplings between your different spins, if you choose them in a particular way, which is set by the pattern that you want to try to learn, okay? So suppose you want the pattern at the bottom of this well to be this image, okay? This image is just a black and white image, so you can just read off the pixels. It's just 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, then 0, 0, 1. So it's just some bit string here. And if you want the bit string at the bottom of this well to not be whatever random pattern was given to you in a spin glass, but you want it to be the image of Hopfield, or you want this minima to correspond to the image of Anderson, and this one to correspond to the image of Parisi, well, there's a way in which you can set your coupling constants so that these are the images that are encoded at the bottoms of these wells, okay? And then, if you recognize, if someone gives you not this version of Hopfield, but a slightly different one or a corrupted one where half the bits have been removed, you can still find your way back and recognize that that's an image of Hopfield, okay? So this picture here really bridges the gap between classical bits and neural networks, and it again shows us how distributed interacting components can create systems capable of learning and memory, which sets the foundations of modern AI, okay? And while modern neural networks have grown much more complex than these simple models, at its root, they still echo these fundamental principles, okay? That robustness comes from this encoding across all of these different degrees of freedom, and that simple units interacting with each other can nevertheless give you emergent memory and emergent reasoning. Okay, so here's a little timeline of kind of the things we've discussed so far, which is the first quantum revolution and the foundations of band theory, which were laid from the 1900s to the 1925s, and then about 25 years later is when the transistor was invented, and then over another period of 20 to 30 years, computers really became mainstream, okay? And now, if you think about AI systems, very, very early ideas in neural networks were developed in the 1950s. Some of these were shown to actually, that there were some fundamental issues pointed out with some proposals here, which led to a long period called the AI winter, okay? And then the foundations of what we recognize today as modern neural networks were laid by Hopfield and Hinton in the early 80s. This was the Nobel Prize from last year. And once again, it was a good 30, 40 years before the technology that comes from these foundational developments has now captured our popular imagination. Okay, so fundamental insights will almost certainly lead to some dramatic improvement in all of our lives, but it can often take 30 to 40 years or a long period for that to actually come about. Okay, so now I want to talk about the thing that I'm most excited about, okay, which is pushing beyond classical systems. You know, even though as I told you, it was the first quantum revolution that led to this era of our modern era. But the modern era is the era of classical computers and of classical artificial intelligence systems. Okay, so now I want to push beyond that into the dawn of the second quantum revolution, okay, which is kind of where we are now. So this is a new era that we're entering, and the defining feature of this era is that we're once again talking about systems of many, many strongly interacting quantum particles. But now, instead of thinking about some system of electrons in a material where you have ways to describe what that system of electrons is doing, but you're not going to control all of those individual electrons in that system, right? It's just the system is what it is, and you're going to understand it and describe it and use it. But here, in the second quantum revolution, the defining feature is that we have exquisite control over individual quantum entities, okay? We can manipulate individual quantum entities, which are still part of some big many-body system, with remarkable precision, okay? And this is important, again, as a matter of principle, okay? Because for scientists, our role isn't just to passively observe and describe nature. Our role is also to create and shape and mold nature, right? And here, and you know, the built universe that we've built or the built universe is a testament to that. But here we're going in and we're really controlling individual quantum entities. So we're going into to the guts of it, and we're exerting this level of control. And once again, we're now going to want to see if you can go in and control things with this level of precision, what are new kinds of emergent phenomena that can arise, and what are new kinds of technologies that can arise, okay? And indeed, like, my perspective on this problem is more that of a many-body physicist. You know, I see these types of systems, and I'll show you some examples in just a slide. And to me, they raise amazing, exciting new questions in what new phases are possible, okay? But really, a lot of this work to build systems like this were motivated by ideas in computing, and go back again several decades to kind of concepts introduced by people like Feynman, who talked about building quantum simulators. Feynman was the one to say, if you want to simulate quantum systems, which are extremely complex, representing the state of some many particle quantum system requires exponential resources. Okay, if you want to simulate a quantum system, well, then build a controllable quantum simulator. Okay, don't try to simulate a quantum system on your classical machine, because you're going to run out of steam very quickly. And then around the same time, in the early 80s, Deutsch laid the vision of really what a quantum computing device could look like. And in the early to mid 90s, there was a lot of work that went on in quantum algorithms, in error correction, in building the first qubits. You know, theoretically, this was the work of people like Peter Shor, okay, who discovered Shor's algorithm for factoring integers using a quantum computer. So, you know, it was this set of ideas going back about 20, 30 years, which really motivated this remarkable progress that's happening today in our ability to control and build these quantum devices across a range of different platforms and across many, many different groups in both academia and industry. A lot of it was really motivated by these questions and the attempt to controllably generate and use quantum entanglement as a resource or as a fuel to gain advantage in tasks such as computing or sensing or cryptography. Okay. So just want to show you a pretty, what I think is quite a dramatic video. This is from Misha Lukin's group at Harvard. And he is building a system of, he's trying to build a quantum computer using a system of neutral atoms. Okay, so you have an atom has many energy levels. Again, remember these are quantized. You can pick up some levels of these atoms and you can use them to define a qubit to store information. And now what you're seeing here is a video where individual atoms can be controllably picked up, moved around, made to interact with other atoms according to the rules that you want, okay? And this can be done in, the very few atoms that are being shown here, but this is really done in systems of thousands of atoms, okay? I think the current limit was 6,100 atoms from Manuel Endres's group this last year, okay? So the level of control here is just incredible, and why do they need this level of control, right? Like, if you're trying to build a quantum computer, you want to run a quantum algorithm, okay? Now, what does an algorithm do? An algorithm takes in some input state, acts on it in some way, okay? If you were running a classical algorithm, you'll act with classical logic gates like AND gates or OR gates. If you're running a quantum algorithm, you want to run quantum gates. But a quantum gate is nothing more than a controlled interaction between quantum particles, okay? So if you want to use this system in order to do something useful, like run a quantum algorithm, per force, you need to be able to have this level of controlled interaction where you can manipulate the system with different interactions in time and take in some input and get out an output, okay? And an algorithm is fundamentally a non-equilibrium quantum process with a great degree of control that is implicit in there, okay? So people these types of developments. I was only showing you a video from a system of neutral atoms, but there's actually a host of different platforms where these types of quantum simulators and quantum devices are being built. And again, I titled this slide "Emergent Qubits," because once again, you have some physical system. This is a system of atoms or, a system of superconducting Josephson junctions with billions of electrons or a system of ions. And then you're going to use those degrees of freedom to bring about, to encode some effective emergent degree of freedom, which you're going to call a qubit, okay? So a qubit, a bare qubit, okay, is some spin 1/2 particle, okay? And the spin 1/2 particle, again, lives on lives on what's called a Bloch sphere. It can be in a superposition of 0 and 1 states. But in these physical implementations, you take an atom and you isolate 2 of its energy levels, or you take a superconducting Josephson junction, and once again, you look at its energy spectrum and pick out some 2 levels and say that that's going to be your addressable qubit, which you can address with some light of some particular frequency, or you can do that with the levels of your ions, okay? And this is the reason I'm mentioning this is because in the very next slide, I'm going to talk about the need for error correction, okay? And this is a fundamental thing that's driving a lot of efforts right now, that's necessary right now to do anything useful with these devices. And you can already see a hint for why you would need to do error correction from these pictures here, okay? I've just picked out for you 2 levels of some multi-level atom, and I've said I'm going to take these 2 levels and I'm going to pretend that everything else doesn't exist, and I'm going to call this my qubit, okay? But again, your qubit is based on some real physical implementation in some real physical system. So even though you want your qubit to be only composed of these 2 levels, well, too bad, because all of these other levels exist and they're going to interact with your system, and they're going to destroy some qubit state that you might be trying very hard to protect, okay? So qubits, just by their nature, are much, much more fragile than classical bits. Okay, a classical bit is either on or off. You can set some voltage cutoffs for what you call on and what you called off, and you can robustly proceed with millions and millions of calculations without getting any failures in your transistors or without any need for error correction. On the other hand, this quantum bit is this very, very delicate superposition. Okay, so this is the famous Schrodinger's cat, which is a superposition of many, many particles. Okay, the cat is supposed to represent a many particle superposition. Here, I've only shown you the superposition in the states of a single particle. Okay, a many particle superposition is even more delicate. Okay, this many particle superposition is what you leverage to gain an advantage in computation, but this superposition is extremely easily destroyed. Okay, anytime you make a measurement on a quantum system, you collapse the superposition. So when you open the box, or a rat sniffs by the box to try to deduce whether the cat is dead or alive, you've collapsed the wave function, and the cat is then dead. Okay? So likewise, even if you yourself are not explicitly measuring your quantum bit, any stray interactions from the environment will make a measurement on your system, destroy your superposition, and this is what's called decoherence. Okay, so you will lose this quantum coherence that's so essential to computing. And indeed, this is some recent review that I found of various different platforms and different fidelities of how much error is there in a 1-qubit gate or just in a qubit hanging out by itself. Okay, and you can see that all of these are in the kind of 0.1% range of error rates, whereas to build a useful quantum computer, we need roughly 10 orders of magnitude better than that. Okay, so these are remarkable systems, but they're still far, far, far too noisy in order to do anything particularly useful. Okay, so this is where the idea of error correction comes in. And once again, we're back to emergence at a higher level. Okay, so we have some system of many particles which gives us this blue dot. This blue dot is what I'm calling a noisy physical qubit. Okay, those lightning bolts are my noise. And now what's amazing is that you can take a system of many, many interacting noisy physical qubits. And you might think that, like, okay, if one noisy bad qubit is bad and I have 100 of them, that's even worse, right? But again, what's amazing and what comes about from emergence is that you can take 100 or 1,000 crappy qubits, and if you get them to interact in just the right way, then an emergent collective state of all of these different many, many qubits can give you a much less noisy qubit, which is what we call a logical qubit. Okay, so we have these many noisy interacting physical qubits, and the collective state of many of them, you ignore where it may come from, gives you a less noisy logical qubit. Okay, so the foundations of this prescription, once again, go back about 30 to 40 years. And it's in the basis of this is the huge and very, very exciting field of topologically ordered systems in many-body physics. So certainly, I won't have I won't be able to explain to you what topologically ordered systems are, but let me tell you a couple of key features. Okay, so this is supposed to represent a Hamiltonian. Okay, this is a Hamiltonian again with some interactions among your qubits. So each dot here is one of your noisy, crappy qubits, and you've set up some controlled interactions between them. Okay, that's your A and your Z. These are these 4-body type interactions. And now, what a topological system has is the property that you can have. We're always interested for this part of my talk, not later. We're always interested in kind of low energy properties of these types of Hamiltonians. So in these topologically ordered systems, you have ground states. Ground states are the lowest energy states of your system. What you find is that if you put your system on what's called some non-trivial manifold. Okay, so suppose you put your system on a torus. A torus has this winding. Okay, it has these 2 holes which you can wind around. Okay, And what you'll find is that the ground states that you get for your system placed on this torus looks locally indistinguishable everywhere. Okay, so if you look at a small patch of your, these are what the ground states are supposed to draw, okay? If you look in a small patch of your 4 different ground states, on a torus you have 4 ground states in the system, and if you look in a small patch, you can't tell the difference between them. But if you look globally across the entire torus at what this winding is doing, okay, this is the kind of cliched example that everyone uses, is that you have a donut and you can continuously deform your donut to turn it into a coffee cup, okay, without it losing its topological feature. So now, if your quantum information is encoded in this global topological feature, but it's locally, if some local noise agent, noise acts locally, okay, you have your system and something's trying to poke it this way and something's trying to poke it that way. If local noise cannot learn what state you're in, and you have to look at some global collective encoded property which cares about the topology of the system to deduce what state you're in, okay, well, then you can become more robust, okay, because you can have lots and lots of local noise, but you can be resistant to that local noise because your information is actually distributed across the entire system in this collective property. Again, this is very, very parallel to the idea of the neural network, okay? Any one individual qubit, you can poke it, you can prod it, you can do your different things, but the number 4 is encoded, distributed in the distributed interactions among the entire network. Okay, so it's very much the same here. So here you have 4 different ground states. These are distinguished by their windings across this torus, and these 4 different ground states can be used to encode the logical states of 2 logical qubits, which is up, 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 down, down, up, and down, down. Okay? So 4 ground states give you 2 logical qubits, and these being collective states, these logical states are now supposed to be much more robust. Okay, so the theoretical prediction by Kitaev, and Kitaev wrote down this thing called the toric code. This is a code because it encodes information, okay, into these robust global degrees of freedom. He wrote down this model in 1997, but his model is really one point in a much broader phase diagram of what's called a Z2 gauge theory, which again had been developed in works going back many, many decades, even before Kitaev's work. Okay, so what Kitaev's prediction says is that actually, if you throw in more and more and more crappy qubits, okay, so you're making your system bigger and bigger and bigger, well, then your information is being encoded over more and more and more of these long scales, so it's even more robust, okay, because some noise agent has to go and really sense the entire length of the torus to be able to tell which state it's in. So the bigger you make your system, the more robust your noise becomes. It's very counterintuitive if you think of it as like just piling on more crappy qubits, okay? But if you think of it as this non-local encoding, then it makes sense. So this was a proposal that's been well understood since the 90s, but again, it took over 30 years or nearly 30 years for this to be seen experimentally, and this was the paper that came out, or that was published just last month from Google, which some of you might have seen. So what they showed for the first time was this promise of error correction, which is that the logical error rate, that's what's plotted here. The surface code distance is just a proxy for the system size. What it's telling you is that the logical error rate is decreasing exponentially as you increase the number of your physical qubits. Okay, so you make your system size bigger and bigger, and your logical qubit is getting better and better, and you can see that this logical error rate is actually now 10 to the minus 3, whereas your physical error rates were more in the 10 to the minus 1, 10 to the minus 2 regime. Okay, so So in this system, they had something like 50 to 70 crappy qubits, and from that emerged 1 qubit. That's what they have so far. They have 1 qubit, but with this suppression. But the really key thing about this paper is this exponential scaling. That if they increase the distance, if they increase the number of qubits, that the logical error rate goes down exponentially. Okay, so this was the key demonstration. And really, again, the number of years, the topological order was formulated in the 1970s. Kitaya's error-corrected code was written down in 1997, and it's now in 2024 that we finally reach this milestone of seeing this error-corrected qubit. Okay. So now you can see all the different layers of emergence that are needed to head towards this holy grail of a what's called a fault-tolerant quantum computer. A fault-tolerant quantum computer is robust to noise. You again start from some system of many interacting electrons. It gives you one noisy physical qubit. Then you get many, many noisy physical qubits to all interact with each other. That gives you a much less noisy logical qubit. And then you have to scale this up more and more and more, so to the point where this much less is several orders of magnitude lesser than even what it is right now. And then you get all of these logical qubits, many interacting logical qubits to all interact with each other, and then you get this fault-tolerant quantum computer that you might be after. Okay? And we're currently many, many orders of magnitude away from this. Okay? So now I want to take a few minutes and go on to just a few minutes of what's next, okay? But I just wanted to pause here, and I've talked about a relatively small corner of physics. I haven't touched any of astrophysics, which Roger's lecture will be discussing. But even in this relatively small corner, the spectrum of accomplishments and developments here is just amazing, right? Okay, so in the last few minutes, what I want to talk about is, we're many, as I was mentioning, we're very far away from this goal of a fault-tolerant quantum computer, okay? Even if we get there, there are very few problems for which we know it's going to be useful. Factoring is one of them. There's very few other examples, okay? But even now, even in their current noisy, crappy state, these devices that are being built are already spectacular new examples of new types of physics experiments, which are inspiring us to ask questions about quantum matter and about interacting many-body quantum systems in regimes that we simply never did before when we were studying quantum materials as they exist in nature, okay? So quantum computers are novel physics experiments, and they beg this question, which is what new phenomena would arise if we could make individual quantum particles controllably interact according to rules of our choice, okay? And I'll emphasize here that everything that I discussed today, all of these amazing phases of matter, literally all stuff on Earth, all quantum materials, all of these exist from electrical charges, electrons, atoms, ions, self-assembling into different emergent structures, describing the phases of equilibrium states in nature, okay? But the set of all states in Hilbert space is a huge space. The set of all states is vast, and the most general quantum mechanical description of a physical system is that of unitary time evolution interrupted with quantum measurements. It's fundamentally an out of equilibrium description, okay? So the set of quantum states corresponding to equilibrium phases is a tiny, tiny corner of what's possible. And what's really exciting is that in these new types of devices, which, once again, this algorithm that they're implementing is fundamentally a non-equilibrium process. And if they can just pick up atoms and get them to talk to each other and interact with each other however they want, okay, then any geometry can be engineered. We're not limited to Euclidean geometry, so you can ask what new phases are possible, okay? And so this is what I've been doing for the last decade or so and had a lot of fun doing it. So you can ask about phases that are fundamentally out of equilibrium. Time crystals are one example of one such phase. You can start asking about phases which are in fundamentally non-Euclidean geometries. So a paper that we posted just last month, which I'm extremely excited about, is a topological quantum analog of this type of spin glass phase that I mentioned to you, which is now capable of storing not classical bit strings or classical patterns like a picture of a cat or of Hopfield, but it stores fundamentally many-body entangled quantum states, which can encode quantum information, just like those topological phases that I showed you. Okay, so this points to this very, very nice kind of fortuitous circle where we have these amazing engineered quantum devices which have been motivated by the quest to build these quantum devices, to build quantum computers, but they're also fantastic new physics experiments which are opening up new frontiers in many-body physics, which should hopefully give us new fundamental insights that in turn will inform the design of these devices. And the two things that are very, very, I didn't discuss it, but I briefly mentioned about time crystals and these non-Euclidean geometries, these are already closely related to some new families of error-correcting codes. The code that I showed you from Kitaev was written down in 1997. Now people are starting to talk about dynamical or space-time codes where you manipulate how the information is stored and processed by changing your interactions and your measurements in time. And these kinds of Floquet codes or space-time codes, they turn out to be a type of topological time crystal where the physics underpinning these codes actually goes back to the physics of thinking about phases of matter out of equilibrium. And when you work in these different geometries, it turns out that you can encode information much more densely and much more robustly than you can with this Kitaev model. Okay, so you can make it much more resistant to errors, and you can pack in many more logical qubits for a fixed number of physical qubits. So these new insights from many-body physics are already going hand in hand with new approaches for manipulating quantum systems to store information and process information more effectively and robustly. Okay, thank you.
Thanks, Vedika, for absolutely wonderful talk. I mean, I wouldn't believe that it's possible to explain error correction in such a beautiful way. So I think we can take some questions. Yeah, so please raise your hands if you have questions. And yeah.
Thank you very much. That was an excellent talk. Thank you for that. And thank you for dumbing it down for people like me. I'm a medical doctor, so I'm particularly interested in terms of any applications or advances you would anticipate in this area. And more importantly, I'm an equity investor. So if there is any specific industry or sector I should be interested in, or if you can be more specific, any company I can invest in. Thank you so much.
Okay, so I'll quote a colleague of mine at Stanford who's an experimentalist and much more grounded in the real world than I am. So especially for, quantum computing is just one application of these types of quantum devices, right? There's a lot of work that's happening in things like quantum sensing. So this friend of mine, his quote was that in the future, just like right now, all devices are small, they're nano. But we've even stopped affixing the prefix nano to everything, right? So in the future, all technologies, very ubiquitous technologies. You may not hear about them all the time, but sensors. So he works a lot in medical sensing, in just using your breath to analyze different, look for different compounds, analyze for different diseases. So he's working a lot on quantum sensors, and that's an example in the medical field where these types of developments can have dramatic impact, even if it's not a functioning quantum computer, right? So I think there will be a lot of things like that will come about. As I was showing you from these different timelines, right? Like the delay from fundamental ideas to practical applications is often 30 to 50 years. So I'm pretty confident that whatever we're working on now will lead to some exciting things in the future. But as of now, I couldn't tell you what to invest in based on anything that I'm working on. Yeah.
Yeah. Yeah. So, yeah, thank you for a lovely talk and explaining very difficult things in a beautiful way. I had a question about the error correction approaches that you described.
Right.
And on the face of it, it's really something very new and with no connection to sort of classical error correcting approaches a la Shannon. Is there a connection, or could there be a connection that you could think of that would be useful, or this is really a different set of problems with different solutions?
No, there's actually a very, very, very deep connection. And in fact, these quantum models that I wrote, that I was telling you about here, these new types of codes, there's something called low density parity check codes. And classically, those are the codes that are there in telecommunication wires everywhere. And now in the last 4 or 5 years, we've figured out quantum versions of them, not we, but computer scientists. But they're close cousins of, in terms of the geometries that they live on, the graphs that they live on. So the way to think about it is the simplest example of a quantum error correcting code is a magnetic hard drive, okay? You have a phase of matter, which is a magnet, okay? There's a collective state. So if you want to encode a 0 or 1 bit robustly, you say that, okay, I'm gonna look at some Ising magnet which is interacting, and then if my ferromagnet has 2 states, which is globally all up and globally all down, and I use that to encode my up and down states, then even if some bits get flipped or fluctuate, you can still recover what that information is. So that's exactly, so you now have a classical Hamiltonian, and the ground states of that classical Hamiltonian are your all up and all down states. And then you can be robust to fluctuations about them, but you use those classical ground states to encode a classical bit. When you want to try to do this quantum mechanically, you need a different phase of matter. So the principles that are common is that you need a ground state which is degenerate and which collectively encodes some property. The things that are different are that for the quantum problem, because you want to encode coherent superpositions robustly, you need these states to be locally indistinguishable. Whereas for a classical model, a magnet, you can look at it and you can say, okay, this region is up and that region is down, so it's not locally indistinguishable. But the underlying philosophy of take a many-body system, look at its phases, okay, is it a magnet, is it a topologically ordered system, and then encode information in that non-trivial phase is universal across these approaches.
My question is, like, what's the future? Will quantum computers be our future? Would we use them in our daily lives? How would it affect our lives?
Yeah, so I think given the rapid scale of developments, I'm pretty confident we will have a quantum computer in the next 10 to 15 years. But the classes of problems that we know quantum computers to be useful for, those are problems having to do with cryptography on the internet or secure when you type in your password to a website, how does it securely get you access to your account? So those are the types of problems that it's known to be useful for. And I think by then we'll come up, or we already have lots of approaches for new ways to get around those problems. But I don't think you'll have a desktop quantum computer which you'll use to do anything in your daily life. But I think there could be other kind of applications that it could be useful for.
Hi, thank you for the session. I had one question about the time crystals that you showed.
Sure.
So those are the topologies which were created for error correction, or are they used in error correction? So are there an outcome for the quantum error correction?
Good. Okay, no. So time crystals is very different from anything that I showed you so far. What I was trying to say is that you have these, so the type of model that you would write down for a time crystal is a set of spins. The spins are interacting in some way. Those interactions are changing in time in some way. And then the system is responding in some other way, which gives you a kind of dynamical phase of matter. I have a few slides that can explain that if you're interested, but it's not got anything to do with error correction right now. So the point is that in trying to build an error-corrected quantum computer, which is now 10 orders of magnitude away, we have already built systems where you can controllably get quantum particles to interact with each other. So even though they're not useful for quantum computing yet, they're already today useful as new kinds of physics experiments, which allow us to ask different types of physics questions about new phases and new possibilities. So this is separate from error correction, but just like other phases have been useful for error correction, ideas coming out of time crystals are useful and are already part of some new types of error correcting codes, which is not the one I showed you, but so new phase can inspire new methods for error correction.
So it's basically a spin-off from an existing what we found out. From that, we took it to a different sort of.
So the model and the question is completely new because everything that we've studied so far is in equilibrium. So you're not even asking these types of questions about you have a driven system and it's many body, and now what are the phases that it can display, and what are the phases that it can display in time. So the system is totally different, the question is totally different, but we're asking this question because we now have access to the system which can probe these regimes.
Excuse me, ma'am. Here.
Oh,
I have a doubt.
Yeah.
Thank you for your inspiring and futuristic talk. This quantum matter equilibrium states, can it be applied to bionic chips, like helping handicapped people? And there are new chips like Neuralink chips, and can it be merged with AI computing? What is your point on that?
Yeah, so as far as I know, there aren't any convincing, there isn't a convincing case that I've seen made for quantum and AI coming together in any way. I mean, people are working on it. That's not to say this couldn't happen in the future, but as of now, I don't know of a clear-cut case where quantum computing could help with those types of problems.
Okay, thank you. And another question. Sorry. Another question is, if we are controlling the non-equilibrium states, are we moving towards, sorry to tell it, are we moving towards a civilization 2 kind of stage?
I mean, I think with AI, we're already moving towards civilization 2. So, yeah, no, you're right in the sense that like, it is really a paradigm shift from like these types of models that I'm talking about and that I spend my time studying. They simply don't exist in the wild in nature. It's a question that I'm asking only because I have access to these systems now. And then it's going to be relevant for a reality that lives in these systems, right? So, yeah, I
think you had a question. Yeah.
Actually, I have two questions.
Yeah.
First is,
It's not on.
yes.
Just bring it close to your.
Yeah. So in the beginning, you showed a slide about the Moore's law. So
Yes.
currently, we are seeing that the semiconductor processes, they are like the geometry is going down, like 3 nanometers, 2 nanometers, and so on. So, and as the geometries go down, we know that the computation needs more power.
Right.
And whether the geometries can handle that heat and the other energy.
Right.
So, what is the future of semiconductors when quantum computing takes? Like, will it go down even more, or it will stop at some point?
When quantum computers take over? Or?
Yeah.
Oh, I think they're just solving very different. So the limitations on that are coming from physical reality on Moore's law, those are real. I'm furthest from the person who can answer how we might be able to make the engineering improve, whether we can make any more engineering improvements or we're really hitting a wall. But I think quantum computing is a separate question because the vast majority of tasks that we're going to be doing every single day, we're still going to do on our classical computers. So I don't think quantum computers will change that fact.
Okay. Actually, my second question was, you showed like the error correction improves if you consider the toroidal topology as compared to Euclidean.
Torus is still Euclidean. Non-Euclidean is kind of these negatively curved hyperbolic things, but it's a non-trivial topology. Yes. Yeah.
Oh, okay.
Yeah.
Okay, so we'll just take a few questions, online questions, and then come back.
Sorry,
Just
he was
please raise
finishing
your, keep your hands
he was
raised so that I
finishing his
can
question.
see.
Yeah. So actually, what I was saying that torus has got a one hole.
Yes.
So in that case, in that sense, the topology is different.
Yes.
So if that is improving the error correction, what is it possible to move to manifold which has got 2 or more holes?
Absolutely, absolutely. So indeed. So the more holes you have, and some of what I was saying with these negatively coded geometries and so on, it's really just asking how many topologically non-trivial kind of holes you have, and each of those can be used to encode some information. But absolutely, yes, that's the principle of it.
Thank you.
Yeah.
Okay, we'll come back. We'll just take a few questions online and then, okay, so there's a question from Subrata Saranglin regarding Kitaev's toric code. Are these 4 the only possible representations of the ground state of the system? I guess there can be many more representations.
Yeah, so there can be many more representations. With the qubit, the point is that with the qubit, so I chose to write my ground states in terms of the logic, in terms of the states of these logical qubits. So these logical qubits currently are up, 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 down, down, up, down, down. But the logical qubits, let's just do one qubit for ease. Okay, the logical qubit can be in any state. It doesn't have to be in up or down. It can be in some superposition of up and down. That's the point of making this kind of quantum code, to be able to encode this logical qubit. So when your logical qubit is in any state, which is any superposition, those will still be ground states of the system, but that's a different representation of your ground state.
Okay, the second question from Gurcharan Singh. What about tensor networks? In some cases, still it performs better than quantum computing.
Yeah, so I didn't make any statements right now about quantum advantage, which is the question about tensor networks or classical computers performing better. There's very few problems again, and they're very abstract, kind of more, they're not very useful for anything, where you can show that there is an advantage to doing a task on a quantum computer, and even there you kind of show that there's an advantage, and then classical algorithms get better, and very soon that advantage disappears. So right now I think the leap that I find more inspiring is more conceptual, which is that I'm asking questions of many body physics about dynamics, about these geometries, that I would not ask if these devices did not exist. Not that these devices are allowing me to do something, to examine these systems in a regime that my classical computer wouldn't be able to examine it. But it's just what I'm a physicist, so what's a physical question to ask? And these devices have expanded the regime of what's a physical question to ask.
There's a question from Della Massonis. Is a higher distance code necessarily better, or does having a less noisy physical qubit better?
I think it's a trade-off with what you're ultimately going to want to get to some logical error rate of 10 to the minus 10. So you can, and in fact, these 10 orders of magnitude that Google has to and other companies have to surpass to get to a useful computer, they're working on all of that. They're trying to make better physical qubits. They're trying to improve the code distance, because each factor that you get, shows up in this exponent and can help you. So I think it's both. You just plug in numbers. Yeah.
Okay, yeah. Thank you for the nice talk. You mentioned about Landauer eraser principle. So I was wondering if you could comment on whether similar fundamental bounds can be also applied to the learning process for a neural network or a machine. And yeah.
I would think so, but I'm not sure. Yeah.
Thanks.
Yeah.
Yeah.
Yeah, I would think so, because it's just information encoded, and if you remove some information that's encoded, then you pay that. Yeah.
Good afternoon, ma'am. Yeah. What, according to you, are the major contributions of the CERN super collider in Geneva in the field of quantum mechanics?
In the field of quantum
mechanics. What happens at the LHC?
This is very far from my. I will defer to some expert on particle physics who might be in the audience. Is there one? I don't know.
Okay, I think Poonam has a comment or question.
Yeah, so it depends on what you're asking. You know, this World Wide Web, it started from CERN, so which you are all using, right? That's one thing. Then, of course, all the particle physics information that you're extracting out of that collider, you're reaching the highest possible energies of 17 TeV. Now, if you want me to explain what a TeV is, TeV is the energy of if we try to convert it, it's the energy of a mosquito. But you know, if you calculate it like calculated thinking that what is the mass of a object and the kinetic energy is something like half mv square, it turns out to be the energy of a flying mosquito. The surprise is that you are putting all that energy into an entity which is much, much, much smaller than a mosquito. So that's the very surprising thing. And a lot of things have come out of CERN, in particular your World Wide Web and a lot of medical applications, TEM, etc., have also come out of that tomography. And
Thank you, ma'am.
Okay, hello. My question is about the non-Euclidean quantum matter, is what you said. Is it something that's merely coming from the topological analogies which we are using? Or is it something that we can physically see on quantum computers in the real physical world?
Yeah, no, it's an actual physical system. So you know, if we sorry, let's go to this slide. So you know, when we talked about spin glasses were, you had classical bits, zeros and ones, which were interacting via some random interactions. A network, right? Like a network, which is like a neural network or a spin glass where you have these interactions between your bits, those are not constrained and those do not live in three-dimensional Euclidean space. They can be on a general graph, right? So when you look at this model on a graph, what you found, or what people found with spin glasses, is that you got this complex energy landscape, and at the bottoms of these wells was some classical bit string, and those are your encoded memories. But why should we look at just classical spin glass models on these general graphs, when now we can put quantum problems, we can make them interact via these general graph interactions as well, right? So classically, we looked at these because, well, it was fun. One, it's fun to look at, and second, like on your classical computer, you can just get them to interact however you want. You can get your bits to set up. You can set up any graph of interactions you want. Now I can do that with quantum particles as well. So I'm going to have a quantum Hamiltonian and qubits that are going to interact on this graph. And now I want to ask, what are new phases? Hello. So a phase that we found is this topological spin glass, where once again you get this rugged landscape, but now these states here are actually locally indistinguishable, like those surface code states, but they're also highly entangled, and there's no classical description of what's happening at the bottoms of these wells. So it's really, I'm really excited by this, because, you know, spin glasses have had so much influence in so many different areas, from optimization to computer science to AI, and this is now like a genuinely quantum version of a spin glass, and I hope it'll be useful for something, but I don't know what that is yet. Yeah.
Yeah, okay. Basically, what I want to ask is, because these quantum computers operate at very low temperatures, are there any advancements in that direction? So a little more higher temperature with these quantum computers working at, is there any advancements in that field?
Not that I'm aware of, no. I think you are stuck at pretty low temperatures, yeah.
Yeah, we can take your question and then the next.
Yeah, so yeah, it was a great lecture. Yeah, here.
Oh.
Yeah. So I just had a small question. So stop me if I'm wrong, but the Copenhagen interpretation, right? There are like two great interpretations, Copenhagen and the pilot wave theory by Dirac. Yeah, so we always consider for any quantum processes the Copenhagen interpretation, right? So if we were to change our look, and if we think that nature is not indeterministic and it is deterministic and it's guided by the pilot wave, according to Dirac, like, will it change anything about the quantum computers, or will it hinder us, like anything? Will there be any change?
I mean, okay, so there's no local deterministic model of quantum mechanics. You have to give up on locality.
Okay.
Right?
Right.
So there's no local hidden variables theory. So, and that's been tested, that
Right,
like
yeah.
Bell's inequalities have been tested to
Yeah.
death. So if you want to go towards a hidden variables theory, you have to give up on locality.
Okay.
And that's so baked into everything that we do that it would require, I think, a big conceptual shift, because
Okay.
we do treat locality of interactions pretty intrinsically in everything. that we
Right.
think of.
Yeah.
Yeah.
Thank you.
Yeah.
Okay, maybe one last question.
Hello. Thanks for the nice talk. So I wanted to know, nowadays the artificial intelligence, they are trained with classical machines, right? Not quantum bits.
Yes, yes.
So
yeah.
Would you expect any advantage in training them with, say, qubits or quantum bits?
So there are people, like a colleague of mine at Stanford too, he's working on this. So there are people asking that question. Right now, it's a research problem. And I mean, even this thing that I'm saying here, this is a version of a quantum spin glass, which is very, very quantum in the sense of these entangled states here. Could this be useful for some type of problem? I don't know. People are asking that question. I don't know of an advantage yet. There's like another question that kind of unsettles me with this stuff, which is like everything around us, all our data is so classical. Like every stream of text, every picture, everything is classical. So it kind of makes sense to say that, like, okay, we're going to store these classical patterns, and the data that we're looking at is fundamentally classical. But now, when I have this quantum data in terms of these highly entangled, locally indistinguishable states, like, what should that even represent, right? Like, I don't know. Like, what should this, if I want to view this as a neural network, what would it be learning? I don't know. So it's the quantum world is just really not perceived by us on a daily basis. I also find it hard to imagine that. Yeah.
It may be a bit strange to ask, but would you expect that those kind of machines to, resemble human brains better, maybe?
Oh, okay. So now Matthew Fisher started a really exciting field in quantum dynamics by asking if the brain is quantum or classical. And I think I don't think we know the answer yet. So.
Okay, thank you.
Okay.
Okay, so I think people can ask questions in the outside over tea. I just had one question. So, like, I mean, you talked about like the classical bits. We store them in transistors, which are actually macroscopic objects.
Right.
And similarly, the quantum bits seem already macroscopic objects.
Right.
But okay, so right now, what's the size of these objects? And like, eventually, if we want to miniaturize, and so is it possible that eventually we can get to this qubits being already microscopic? Then
so the atomic qubits are just single atom.
Right. Yeah.
So atomic qubits are that.
Yeah. But the ones we use are usually typically macroscopic.
The Google ones, I don't know what I mean, the chip is that big.
Right. Yeah.
And that has about 50 qubits. So yeah.
Okay.
Yeah. So
but eventually, it's plausible that they can be microscopic, right?
I would hope so. Yeah.
Okay, so let's thank Vedika again for really fantastic.
Yeah, so I also just wanted to thank Vedika for a wonderful lecture, and thank all of you for coming again. There was one important thing I forgot to acknowledge at the beginning of this talk. A lot of the support for this and the other outreach event comes from Arista Networks, and they have been a very staunch supporter of our outreach activities, so I thought I would acknowledge that publicly. So thank you very much again, and look forward to seeing you.